Quantitative Big Imaging, Lecture 10, Software Engineering for Reproducible Workflows. And we have been looking now at a lot of image processing, statistics, also plotting today, but there is one thing that we haven't really been looking into seriously, and that is how we actually produce our processing workflow. And there we need some coding. The more strict way would actually be to use some software engineering in order to get our workflows more reproducible and well documented. And for this, there are a couple of books and papers. This paper here is generally written for larger teams, but there is a lot of knowledge also that could be applied for one-person teams or single developers or smaller teams. So it can be used on different things, and it's more general for scientific software, but it applies also well to image processing software. We have from lecture 8, we already talked about repeatable workflows, and I started hinting on some structural things that we could imagine. First of all, we need to have well-described steps, also doing in some analysis, preferably without any magic, and finally we need to document everything we did. And to get the repeatability, we need the code to be testable, and there should also be a tracked history on it, and it should be possible to be reviewed, maybe also by either by a colleague or nowadays also on services like GitHub, there is an AI reviewer which actually can also catch one or the other inconsistency in your code. And finally, of course, you also wanted to have it documented. On top of that, you can also track bugs and add new ideas with the help of an issue manager, where you can log new requests or ideas. And the tools that we want to use to support the reproducible workflows is, first of all, we should definitely use a repository. This is a smart history management that can split off different branches. If you want to get a new idea, you just make a new branch of your development without destroying what you have been doing before. The next thing is we should also use automated tests, and this is kind of our receipt that our functions are doing the right thing. Going really advanced, you can also go for using a build server, and that means every time you push something to the repository, then the automated tests are actually executed automatically, and there is a test that checks that everything is as it should. Then is the question how you organize your code, and in this class we have very much been using notebooks, and they are great tools for prototyping, but as soon as you want to have more structured, easily maintained code, then the notebooks are horrible. Also, submitting a notebook to a repository can also be very confusing, because the executed cells, they contain information that changes from execution to execution, and that is also very hard for the repository to handle these changes. Then notebooks are also not so easy to share always, and testing within the notebook is also a bit difficult and awkward. So the idea instead is to save the main functions that you want to use in your analysis as Python files, which then are imported. So for example, you have your functions in your file mylib.py, and that file must be in the same folder as the notebook or the other code that you're writing. Then you do import mylib, and then you can type mylib.myfunction which takes some parameter, whatever. And while you're developing, in particular in a notebook, it's not easy to get this library reloaded. So you need to use this import lib function, and then it's reloaded when it passes through this line. And then you get the latest version in your Py file. Documentation is essential, and it's very often, honestly, forgotten. There are different levels of documentation. There is the concept of in-code comments, so just telling this block is doing this, or just to kind of structure the functionality of the code. They should not be obvious, too obvious. So for example, there is no point in saying adding variable A and B. It's obvious when you read the code, so that shouldn't be added as a comment. Next level of comments is the API documentation, and that describes which arguments and return values a function has. And that's also what you're using when you type on the Python prompt. You type help and a command, and then you get some documentation. I've shown it also in the lectures in some cases, as you may remember. Final level is the user documentation, and that doesn't describe much of the algorithms themselves, at least not always, but it describes how the code is intended to be used. So it describes workflows, how to call the function, under which circumstances it should be and not be used, and so on. And for reproducible workflows, it is certainly important that the API documentation is present, because even yourself don't know a month later exactly what each parameter means. So let's look at the API documentation, which in Python is done by adding 3 quotation marks in a row and closing it with the same 3 again. Typically you have the description and describes what the function is doing. You have a list of parameters, and you also have the return value. And then the function comes that does something. And if you type help fancy function, this is what you get then afterwards on the prompt. If you work with other languages than Python, there are different tools. One that I have been using a lot is Doxygen, and there you also write similar kind of comments as we did here within the Python code, and it also provides the functionality to provide description, the short description, parameters, return values, etc. And then afterwards you compile it, and you get, for example, an HTML document or also a PDF document with the full documentation of your API. Oops. And let's see, I just need to leave the cell, and here we come. The next thing that I mentioned is the unit testing, and that is code, additional code that you write in order to test different functionalities of your functions. And often the idea is that the unit test should test very small pieces of the code. So don't have a test that do the full workflow that you have, but really small functions like count items or something like that. And there are frameworks for unit testing in principle every language. So many languages have support for this, and you can even do automated testing and reporting of the results. And yeah, Java, C++, MATLAB, R, Python, all of them have some kind of support for this. Then we have a couple of texts that are good to read about how, first of all, a motivating text that you really need to have tests to make sure that your code is doing what it's supposed to. For a screen page of code, it's not so important, but if you come up in tens of thousands lines of code and you start changing something in one region of the code, it may affect several other places, and that is something we want to avoid. And there is what the unit test can tell. This function doesn't behave as it's expected anymore, and then it reports that. There are also some unit testing guidelines if you follow this link. So the design. The first requirement is that you should divide your code up into small independent parts, so the functions or units. And the idea is that each part should be tested independently of the others. And if they're well done, units can be changed and tested all independently, and you can test and focus on just one piece and see that it works. And that also makes the upgrading or expanding your tools very easy. You can be sure that everything is working as it's supposed to. And finally, you do some integration testing, so just checking that everything works together as a long chain. Then how to test? There are two approaches. One is the happy path, and then you check that it does what it's supposed to do. And so if you say you have adding two variables, the sum should be this, the output should be the sum of those. And that is what you're testing. The other way is to provoke your code. That's a bit more advanced and not always so easy to handle. That is when you provide data that will fail the execution. Maybe it's the wrong matrix size, maybe it's that you have zeros and the logarithm is computed and instead you get a lot of infs or nones in the data. That is the kind of behavior you want to test and see how it behaves. And then you also need some test data, in particular if you work with images, and it should be realistic, but it could also be simulated test data, so you can really build up the scene that you want to test on. And as you want the unit test to run very often, you shouldn't have too large images for your test. So maybe you can crop it in 200 by 200 sized images, if that is enough to test what you're doing. So the final comment is that your testing is only as good as you write your test. If you don't write a test to catch something, you will not see it. So be aware that the tests are only as good as you give them. A test example. So let's say we have a function that counts all the non-zero voxels in an image. It's defined something like this. We have a voxel count and send in an image, and the output is then voxel counts. For that, we can write the following tests. We send in test if an image is empty, then count voxels of this zero image. So it's only 3 by 3 zeros, then the sum should be 0. Next one is testing if a 3-dimensional image is 0, and it also should be 0. And this assert command is the one that tells if this test is failing or succeeding. Then we can add another one, for example, diagonal. So count voxels of I. I is a function that produces a diagonal matrix of ones. So here we should also, in that case, get a 3. And what we see here is that the function should work for 2D and 3D images. If they're empty, they should give 0, and if they have something, then they should give the number, the actual number of the data. So here we created actually our test data in these tests. And otherwise, we can look into some kind of shape analysis and to identify the different steps. We can, for example, look into, we have the component labeling, we have analyze objects, that would be a higher level function. That should be tested later in the process. And then we have count voxels, we have calculate center of volume, shape and orientation, and an isotropy, and all these should provide values that we can test individually actually. So if you send to the count voxels, send in an image with some voxels in it, then it delivers that, and that we can test individually nicely. In Python, there are different packages for doing the testing. So there is one which is a built-in Python module, and it's also ideal for the beginners as it's very simple. More advanced projects tend to use PyTest, and it's very flexible and has advanced features, and it's more suited maybe for larger projects. Doesn't say that you shouldn't do it with small projects, but it can handle, it scales up well. And here you make a set of specific tests for each module and run each. You could run it actually each time the project is updated, and that's integrated in the whole framework. So an example, now we can look at, for example, the from scikit image. We have two tests, test watershed and test connected components. And here we have a test class, test watershed. We produce an image, and then we want to see what watershed is doing with it. And here we have a test data array. We have just a hole in the middle here of the ones. And then we have a marker. And actually we have two markers. We have one outside and one inside. And we should see what it does. And then we tell, we run the watershed, and then we say, this is what we expect. And the error is the difference between expected and the output. And then it tests something around if there is an error somehow. And it should be less than this epsilon. The other way is, for example, if we want to do testing within the functions, we can use something called doctest. And here we have started writing the documentation, and at some point it comes to these indented positions where it says run this code and apply the threshold, and that should run it. And that can be used then for this test running. And it's a way to keep it within itself, but well, I would actually personally prefer using PyTest for the testing. Within Jupyter, it's even harder to do the testing, because here everything runs in notebooks and in the notebook cells, but we can use something called doctest and this func tool. And for that we need to define a decorator which is called autotest. And a decorator is a code that is only run once when the function is defined and never otherwise. And what we do when we use it, we do an add autotest in front of the my function, and that corresponds in principle to calling autotest my function, but now it's only called once when you try it, when you create the function. So here's an example where we do this add 5. We have already defined this auto-test function, and then we run it, and we can see here that it's running this docstring test in the function. So here it says add 5 to 5, and the response should be 10. And then it says trying add 5, expecting 10, and that is okay. So this is a way how you can introduce the tests in your notebook. A little bit larger example would be this one, where we do we have again some labeling. We do the I, and we do this array. That's the test image, and it gets the diagonal, and we will label it. It gets in principle only the ones, because that's the only label there is. If we replace the central pixel with a 0, we have a simple label again, and then we can see that we got 2 labels, 1 and 2, and that is what's to be expected. And then we can also see that all the steps, they are okay, so we can be happy with this. And if you want to work with other languages, so for example, if you're working with MATLAB, there is a built-in test framework. With C++, there are many different frameworks for doing the unit testing. I believe the most popular one is the Google test. Then there is the Boost test. Boost is a very large library of support functions, and that to some extent have got their way into the standard library. Another one is Qtest, is from the Qt GUI user interface library. This is actually the one I use because I'm doing my user interfaces with Qt. All these tests, they are managed with the help of a combination of CMake, that's the build tool, and CTest, which can run the tests and do reporting and identify which ones that need to be rerun at some point. And to pull this to its extreme is when you would do test-driven programming. That means, in principle, you define first what you want to do, and then you write your tests, and then after you have written the test, you start writing the actual code. And then you can see how far you have proceeded. When one test is okay, then it means you have implemented that requirement. This is an approach that is not so common in scientific programming or scientific projects. You usually don't want to write a lot of requirements and things like that. So the tests are usually defined after we have written the function, when you want to see that it actually does what it should. So you can also set up some requirement, and the vocabulary that is important when you do requirement is the word shall. That means this function must provide this information. So for example, you can say that shape analysis shall provide an anisotropy of 0 when we input a sphere. The center of the volume should be precise within half a pixel. And you can even bring in benchmark requirements of a 1K by 1K image should be processed within 30 seconds. So now we hopefully have reliable code, but to be sure that the code is also safe for the future, we can use repository. And in principle, it's a backup system that are tailored for the needs of software development. So it can synchronize multiple versions. It can manage development of branches, so different lines of development without disturbing each other. And there is always a centralized server which keeps all the data. And the reason why you should use a repository is that it's easier to go back to earlier versions. So if you have a bug, you can track back and see from the database entries where you changed it and what you did to change it. And then you can compare and go back and see why what happened. It's also good for the reproducibility. You can track exactly what happened. So if you do some development, you publish the results, and then you continue doing development. But at some point, your reviewer is saying, nah, I don't believe it. Then you can go back to the level that you were when you submitted, and you can see, okay, I did something strange here. Also, bug tracking is easier, and if you're many people working on the same code, you can work without disturbing each other. So if everybody are working in their own branches and only at the point when their development is reliable, they push it to the central branch, and then everybody can enjoy this development without being disturbed. And thanks to the unit tests, you can also be sure that it actually does what it should, even when the new things come in. And for repository, you have some basic operations. You have add, that is adding a new file to the repository. And you have commit. And commit means that it's like a timestamp where you say, now this code is, I'm happy with this level of the code, and you can describe it a little bit, saying at this commit I changed 3 files and they did this and that. This is for some repositories systems like Git. This is happening locally, and then you have to synchronize with the central server, and with that you do a push and a pull. The push send up your latest changes or all your latest commits, while the pull fetch what your colleagues have been doing before, or yourself maybe even on a different computer. And it can also create and switch and merge branches. So a branch is a new development. Of course, you can create it. You can jump between them. So if you're working on different ideas, you can have different branches, one for each idea. And finally, you also want to merge branches. So if you're happy with the result, then you say, okay, I want to merge this into that branch. And often you merge it into the main branch so everybody can enjoy what you have done. There are different repository frameworks, and the most popular one today is Git. It's very lightweight and easy to work with. There are also other ones like Subversion, Mercurial, and Perforce, but you can see here from a survey that Git is doing about 90-something% of the whole market of repositories. The other ones, they were popular. So back in for 10 years ago, SVN was pretty popular, but it has phased out completely in principle. So it's below 10% nowadays. Then there are different providers of Git repositories. So we have GitHub, which is the big one that very many are using. It has both a free version, and you have up to enterprise level of subscriptions with different added services. And same is also for GitLab. You can have the same thing there, and Bitbucket and Azure. But it's not only that you have a server, you have a whole environment. And for the Git server, you have first the repository functionality itself. Then you have issue tracking. So it's actually a way to keep track of what you still need to do. It can be bugs, it can be new ideas. And the issues can be used in a project management. What you also can do is having build actions, which I come to soon. And depending on the service you're using, for example, GitHub have academic accounts, which makes it possible for you to have private repositories, which is good if you want to keep your research secret. And there is also the possibility to have GitHub Copilot, which is an AI that can check your code. It can do code reviews. It can even do, you can even use it as an advanced manual. You can ask even related to your code, and it checks if you have a warning of some kind that you don't know how to handle. It finds it and tells what you need to change in order to get it right. It could in principle also do full vibe coding. Vibe coding is when you just tell the AI, I want to solve this task, and it provides some code. I don't recommend doing full out vibe coding. Then you lose the control completely and you don't know what is happening. So that is a very powerful tool, but you need to know what you're doing if you want to use it. That's my opinion, at least. It can be a good starting point, but usually you want to tweak the code anyway. Local servers. Many institutes have their own servers. So ETH has the GitLab. At PSI, we have the Gitea. And other universities, Basel, Bern, Lucerne, they all have their own Git server hosted on the institute. And I have mentioned a lot of times now that you can work with branches, and this is there are different workflows. You can work on a single branch, then it's like just a backup server with comments. But the best way to work is actually to work with multiple branches. And then you split off. You have, for example, you can relate it, like I have done here. Relate it to an issue with a number and then a little description. And you can see here that I have done some changes. I have here some timer issue, which I pulled and pushed a couple of times. I did an extra sub branch to handle something, and then I merged it back here, and then finally I merged it back into the main branch. And ideally, you should never really commit code directly to the main branch, but always work through as sub branch, and in these branches you can do all nice testing and make sure it works, it doesn't break anything. And what you see here is really a typical workflow. You have the side branch, and at some point you're happy with what you have. Then you actually first merge the main branch content into the side branch. And then once everything is okay after the merge, then finally you can do the merge into the main. So with that, you are sure that everything is running smoothly when you push the results into the main. Another tool that is available now in GitHub and also in other repository services is continuous integration. And that is in principle when you push something to the server, it will automatically start some kind of script. It could build the code, it could test the code and see if everything is okay. And if it is, then it gives you a green check mark. Or if it doesn't work, so in this case, I think there was some kind of version clash or something, then you get this red cross and you can't continue. So that actually tells you that before you can do the merge into the main, you should make sure that it's actually running on the branch first, also on the remote. And well, this now we're getting closer to the end. I plan to do also a GitHub introduction where I show really hands-on how what commands you need to do to create a repository, add some files, commit, and do some pushing and pulling, and then creating new branches and switching to them, making changes in the code, and then again merge it back into the main. And yeah, that summarizes the software engineering part. And the important things is always document your code. Unit testing will save you a lot of sweat, in particular if you have a bug in the code. And working with repositories is actually an insurance that your code is stable and that you can go back if you have some problems at some point. Continuous integration is, say, the higher school. Most people are not using it for small scientific projects, but if your code is growing into something bigger, then it's worth considering. And that closes this part of the lecture.